first paper of electronics, that is semiconductor devices and basic electronic systems. This is the first chapter of this paper, that is semiconductor diodes, and in this video we are going to learn about the PN junction diode. What is semiconductor? The materials are called semiconductors materials if their conductivity falls between that of a conductor and the insulator. We can say that semiconductors are neither conductors nor insulators. The conductivity of semiconductor depends on a temperature. As temperature increases, the sensitivity or conductivity of semiconductors also increases. At a very low temperature of the order of a 0 degree Kelvin, that is nothing but the minus 273 degrees Celsius, semiconductors acts like insulators. At a temperature close to 20 degree, the conduction begins in the semiconductors. That means at a room temperature, conduction begins in a semiconductor, and the conduction increases with the increase in a temperature. So what are the different types of semiconductors? So there are two types, that is intrinsic semiconductors and extrinsic semiconductors. Let's see this semiconductors in details. So what is intrinsic semiconductors? An intrinsic semi means pure. So the intrinsic semiconductors are the semiconductors in their purest form. And the presence of impurity, and impurity are nothing but the atoms of other materials, is a very low, as a 1 part 100 million parts of the semiconductors. So the intrinsic semiconductors are equivalent to insulators or a very poor conductors at a room temperature. For example, silicon and germanium. Now, what is extrinsic semiconductors? So this extrinsic means impure. So we can define the extrinsic semiconductors as the semiconductors obtained from the intrinsic ones by adding impurities to them. And the process of adding these impurities to the intrinsic semiconductors is called as a doping. Due to this doping, the conductivity of the semiconductors increases. Thus, extrinsic semiconductors have a better conductivity than the intrinsic semiconductors, and therefore they are used in manufacturing of all electronic components such as diodes, transistors, op-amps, etc. So the types of extrinsic semiconductor materials are nothing but the N-type semiconductor materials and P-type semiconductor materials. So how the conduction takes place in intrinsic semiconductor materials? So this is nothing but the intrinsic semiconductor material at a 0 degree Kelvin. That means we can say that no free electrons or holes are there for the conductions. So when the heat or a light that incident on this intrinsic semiconductor, what happens? Because of this incident light or a heat, the temperature of this increases, and this valency band or the atoms, they are present in valency band, they break the covalent bonds and becomes free for the conduction. So these electrons, after gaining the energy, they move into conduction band. So hence the electron and hole pairs, they are generated because of the increasing temperature. So with this increasing temperature, many valency electrons will absorb the thermal energy and break the covalent bond and enters into the conduction band. So the conductivity of intrinsic semiconductors increases on application of either heat energy or a light energy externally. However, this method of increasing the conduction are not practically usable. Hence, the conductivity is increased by means of a doping process. So the process of adding impurities to these intrinsic semiconductors, that is nothing but the silicon or germanium, is called doping. And the materials which is used as an impurity in the doping process is called as a dopant. So what are the materials they are used for this doping process? First is the donor impurity, that is nothing but the pentavalent impurity. A pentavalent atom is an atom containing 5 valence electrons in its outer shell. So the donor doping is used to manufacture N-type extrinsic semiconductors. For example, phosphorus, arsenic, antimony. Then second type they are used for doping is the acceptor impurity, that is nothing but the trivalent impurity. So a trivalent atom is an atom containing 3 valency electrons. So the acceptor doping is used to manufacture p-type extrinsic semiconductor. For example, aluminum and boron. How the n-type semiconductors they are constructed. So here, this is the silicon, that is intrinsic material is there, and this is the pentavalent dopant, that is phosphorus. So here is the pure silicon atom, then this is the phosphorus impurity, and after adding this impurity, this will form the covalent bonds with the 4 atoms of this silicon, and the 5th valency electrons of phosphorus becomes free. So as we adding the more number of this impurity atoms, more and more this free electrons they are available. So corresponding to each impurity atom, an extra electron becomes available for conduction. Hence, the increased number of electron will make the semiconductor an n-type semiconductor. N means negative, and this free electron is having the charge, that is negative charge, and that's why this is called as a n-type semiconductor. A large number of electrons are present along with a small number of thermally generated holes in an n-type semiconductor, and hence the conduction largely takes place due to the free electrons, and therefore the free electrons are called majority charge carriers and holes are minority charge carriers in n-type semiconductors. Now, how the conduction in n-type semiconductor take place? So this is the n-type material, and this is connected to this external battery. So here the having the maximum number of electrons and the small number of or minor number of a positive charge, that is holes. So when this positive terminal and negative terminal of this battery is connected to this n-type material, so this positive terminal of battery will attract this negatively charged electrons, and this negatively charged terminal of battery will repel this negatively charged electrons. So in this way the electrons they flow, but the conventional current that always flows from positive to negative. So this direction of conventional current is always opposite to that of electrons. So when an external DC voltage is applied to the n-type semiconductor material, the free electrons move towards the positive terminal of the source and holes move towards the negative terminal of the source. Now, how the p-type semiconductors they are constructed. So here again the intrinsic semiconductor material, that is silicon, is taken, and this is the impurity atom, trivalent impurity atom, that is boron, is here. So this boron is an impurity atom. When this added to this intrinsic material, so the 3 valency electrons of this boron will generate the covalent bond with the 3 atoms of this silicon, and here one hole is remains, that is absence of a electron. That means that's why it is called as a acceptor impurity or a acceptor semiconductor. So corresponding to each trivalent impurity atom added, a hole is created, and hence the increased number of holes will make the semiconductor p-type semiconductor, because these holes is nothing but the absence of electrons. That's why it contains the charge positive, and that's why it is called as a p-type semiconductor. And a hole is positively charged as it represents the absence of a negative charge. A large number of holes are present along with a small number of thermally generated electrons in a p-type semiconductor. Hence, the conduction largely takes place due to the holes, and therefore the holes are called majority charge carriers and electrons are minority charge carriers. Now, how the conduction is in a p-type semiconductor material is take place. Again, here we have taken a p-type material where the holes are majority charge carriers and negatively charged electrons they are minority charge carriers, and this material is connected to this external battery. So these are the majority charge carriers, holes, and these are attracted towards the negative terminal of the battery, and these are the minority charge carriers. So when an external DC voltage is applied to the p-type semiconductor material, the holes moves towards the negative terminal of the source and electrons move towards the positive terminal of the source. And the conduction in p-type material is mainly due to the majority charge carriers, that they are nothing but the holes. So that's why these holes are called as the majority charge carriers, and these electrons are called as the minority charge carriers. And again, the directional or the conventional current flows from positive to negative. Now, formation of a PN junction diode. When we connect the p-type and n-type material, we form the PN junction. So after connecting this p-type material with this n-type material, so here the PN junction is generated. So here, after this PN junction, the electrons from this n-type material, they cross the junction and move or recombine with these holes. And after recombination of holes, here some holes are with a positive charge they have generated, and they are converted into the immobile ions, and they are accumulate near the junction. And this will refuse the further depletion or the further diffusion of these electrons, and that's why it is called as a depletion region or a barrier region. So this is the depletion region generated when the p and n type material, they are connected to each other. So these p-type and n-type semiconductor are joined together with the help of a special fabrication technique to form a PN junction. And the blue shaded region on both this side of the junction contains only immobile ions and no free charge carriers such as electrons or holes. And in other words, this region is depleted of the free charge carriers, and therefore it is called as a depletion region. Now the barrier potential or a junction potential. So the electric field created due to the presence of immobile positive and negative ions on the opposite sides of the junction is known as the barrier potential or a junction potential or cut-in voltage. The polarities of barrier potential are decided by the type of immobile ions present on the two sides of the junction. And this is called the barrier because it acts as a barrier to oppose the flow of electrons and holes across the junction. So it is measured in volts. So the materials that is silicon and germanium, so these are the cut-in or a barrier potential or junction potential values. For silicon it is 0.7 volt and for germanium it's 0.3 volt. Now the PN junction diode or a rectifying diode. So this PN junction itself forms the most basic semiconductor device called semiconductor diode. And the meaning of the term diode is the device having two electrodes, and a diode is a two-terminal semiconductor device that allows current to flow in only one direction. So from anode to cathode, and doesn't allow current to flow in the reverse direction from cathode to anode. So this is the PN junction. And this is the circuit symbol for the diode. So it has two terminals, anode and cathode. So this arrowhead of this diode indicate the direction of flow of a current through this diode. And this is the real component appearance, how the PN junction diode is look like. And this is the strip marks the cathode. So this silver strip indicate that this terminal is a cathode. Now biasing of PN junction diode. So biasing is defined as the process of applying an external DC voltage to the semiconductor diode. So it has two types, that is forward biasing. So in this, positive terminal of the diode is connected to P region or the positive terminal of the battery is connected to the P region and negative terminal connected to N region. And in reverse biasing, negative terminal of a battery connected to P region and positive terminal connected to N region. So let's see the PN junction diode in a forward bias mode. So here is the PN junction diode that is connected in a forward bias mode, that is P type is connected to positive terminal of battery and N type is connected to negative terminal of a battery. So this is the circuit, that is we have connected the diode in a forward bias mode. So the negative end of external source connected to the N region will push the free electrons from N side towards the P side. Similarly, the positive end of the supply will push holes from P side towards N side. So this negative terminal will repel these electrons from N side and it push this electrons towards this junction, and this positive terminal will push these holes, positively charged holes, towards this junction. So with increase in the external supply voltage, more and more number of holes and electrons starts traveling towards the junction. As a result of this, the width of the depletion region and the barrier potential will reduce. So if the external voltage becomes more than the value of the potential barrier, that is estimate 0.7 volt for Si and 0.3 volt for germanium, the opposition of the potential barriers will be overcome and the flow of current will start. And hence, large number of electrons and holes will cross the junction to constitute a current called as the forward current, that is IF. And this forward current flows due to the majority carriers, electrons and holes, and its direction of flow, that is conventional direction of the current, is always from anode to cathode, that is from positive to negative. So here we can say that this negative terminal of battery will repel these electrons present in N side. This will cross the junction and recombine with the holes, and in this way the current flows through the diode. So due to a large current, the forward resistance of the diode is very small, typically of the order of a few ohms, that is 10 to 100 ohm only. And the forward voltage drop across a conducting diode is denoted by the Vf, that is forward voltage, and which is equal to 0.7 volt for silicon and 0.3 volt for a germanium diode. Now, after connecting the PN junction diode in reverse bias, so here we have connected the P type of diode to the negative terminal of battery and N type to the positive terminal of the battery. So this is the circuit diagram where we have connected diode into the reverse biased mode. So figure shows the reverse biasing and a small reverse current that flows from the cathode to anode of the diode is denoted by Is because of this minority charge carriers. So thus reverse current flows exactly in the opposite direction to that of the forward current. And when diode is reverse biased, holes in the PN region and electrons in N region are attracts away from the junction towards the negative and positive terminals of the external supply respectively. So here we know that the opposite charges, they attract each other. So here the negative charged electrons, they are attracted towards this positive terminal of battery, and this positively charged holes, they are attracted towards this negative terminal of the battery. So because of this due to increase in negative voltage, the movement of electrons and holes away from the junction will increases. So the width of depletion region increases due to the creation of more number of positive and negative immobile ions. So the P region consists of a small number of electrons and N region consists of a small number of holes, which are the thermally generated minority charge carriers. And the majority electrons in the P region are attracted by the positive terminal of the DC source. Hence, these electrons will cross the junction and constitute the reverse current, that is Is of the diode. And it is also called as the reverse saturation current, and it is very small in the range of a microampere. So the reverse current is a small, which indicates that the resistance offered by a reverse biased diode is very large. As the resistance is large, current flowing through that resistor is very small. So it is denoted by the RR, it is reverse resistor, and its value is in the range of a few hundred kilo ohm. The reverse bias diode is equivalent to a large value resistor, and therefore the reverse voltage across a diode is almost equal to the DC source voltage, that is input we have applied. Now the breakdown in reverse biased diode. The process of widening of depletion region does not continue for a long time. As we increase the negative voltage, the depletion region width will increases, but this process is not or does not continue for the long time because there is no steady flow of a holes from right to left, that is from the N side to P side. So if the reverse voltage across a diode is equal to or greater than a voltage called breakdown voltage, then a large reverse current starts flowing through it, and this is called as a reverse breakdown. a large power gets dissipated in the diode due to the reverse breakdown because of the large current flow through the diode. And the reverse breakdown can sometimes damage a diode permanently. Hence, it should be avoided. So here are the voltage ampere or IV characteristics of the PN junction diode. That is forward and reverse characteristics of the diode. So the IV characteristics of PN junction diode is a graph of voltage across the diode versus the current flowing through it. So here the IV characteristics can be divided into the two parts, that is forward characteristics and reverse characteristics. So let's see first the forward characteristics. So it is a graph of forward voltage VF versus forward current IF. So this is the forward voltage VF versus forward current IF. So this is the forward characteristics. So in this region, the diode is forward biased. So first, that is in the region of A to B. So here from the region A to B. So in the region of A to B of the forward characteristics, the forward voltage is small and less than the cut-in voltage. So this is the cut-in voltage, that is 0.3 or 0.7 volt, and when the input voltage is less than this cut-in voltage, so here the forward current flowing through the diode is very small. So we can say that here initially it is 0 and a very small current that flows through the diode when the input voltage is less than this VF or a cut-in voltage. B to C. Now, as soon as the forward voltage equals to cut-in voltage, current through the diode increases suddenly, and the nature of this current is exponential. So here, from here we can say that as soon as the voltage, input voltage VF, that is equal to this cut-in voltage 0.3 or 0.7 volt, at that time the current through diode will increase suddenly, and this nature is a exponential. That means it is independent of the if there is a small change in the input voltage, there is a large change into the output current. So the large forward current in the region BC of the forward characteristic is limited by connecting a resistor R in a series with the diode, and this forward current is of the order of a few milliampere. Now the cut-in voltage or a knee voltage. The voltage at which the diode forward current starts increasing rapidly is known as the cut-in voltage of a diode, because when the input voltage or a forward voltage is equal to this cut-in voltage, at that time only the diode becomes forward biased and current starts flowing through it. So that's why it is called as a cut-in voltage. And the cut-in voltage is very close to the barrier potential, that is 0.3 or 0.7 volt, and it is denoted by the V gamma. Now the reverse characteristics. So it is a graph of reverse voltage VR versus forward, the saturation current or the reverse current IR or a saturation current IS. So this is the third quadrant where this reverse characteristics of diode are given. So it is the graph of reverse voltage VR versus this reverse current IR. So the current flowing through a diode in the reverse biased state is the reverse saturation current, which flows due to the minority charge carriers. As the reverse voltage is increased, the reverse saturation current remains constant, equal to IO if the temperature is constant. So here we can say that this is the leakage current, or we can say this is saturation current. It is very small in the range of a microampere. As the input voltage or the reverse voltage increases and the temperature is constant, then the output current or reverse current is equal to IO, that is a reverse saturation current. This is because reverse saturation current does not depend on reverse voltage, but it depends only on the temperature. But as the reverse voltage reaches the breakdown voltage value, a large current flows through the diode due to the reverse breakdown. So this is the breakdown voltage. When this reverse voltage reaches to this breakdown voltage, after that breakdown has taken place, that means the depletion region or that barrier will collapse and large current will start flowing through the diode. So this reverse breakdown current that is very high, so the operation in the breakdown region should be avoided because the diode may be damaged due to this excessive power dissipation. Now the peak inverse voltage, PIV of diode, is the most important term, and it is the maximum voltage that can be applied to diode without damaging the junction under reverse biasing condition. Applications of PN junction diode. So rectifying diode or a PN junction diode is mainly used as a rectifier where alternating current is converted into the direct current, which is used as a power supply. Diodes are used in clamping circuits for DC restoration. Then diodes are used in clipping circuits for wave shaping. Diodes are used in a voltage multipliers. Diodes are used as a switch in digital logic circuits used in computers. And diodes are used in demodulation circuits. Now, here are the questions based on this topic. So what are the different types of questions I have given over here. Multiple choices there. Then short answer questions are there. Solve the assignment.